So in this lecture, I'm going to talk to you about how does our body actually start to communicate electrically. Think about most cells don't have electricity flowing through them except for neurons. Electricity doesn't really drive anything in the cell except for the except for the nervous system. So how does it actually happen? And the key to it is establishing what's called the resting potential. So see this picture here, someone might step on a tack. We get electrical signal that travels up through our body and it goes all the way up to your brain, tells you it hurts. Yeah, and then maybe a motor neuron tells you to pull your foot away. Well, how does that electrical signal actually even get started? Well, it all comes down to some basic properties of the cells and neurons. Again, we've got our major thing. We've got our phospholipid bilayer. We have our extracellular and intracellular space. Okay, remember we have those parts that are water friendly on the outside, water phobic on the inside. So it's going to be hard for water to make its way through that bilayer unless something's there to allow it to happen. And here's what's going to do that for us. We've got channel proteins. These channel proteins are going to insert themselves into the membranes. Okay, they're going to have transmembrane domains, which allows them to exist within the hydrophobic and hydrophilic nature of the phospholipid bilayer. And you can see here that they have this opening on the outside that's going to allow for ions to start to move across. Remember, ions are electrically charged chemicals that have been that are either with an extra electron, missing an electron, or have gained an electron. Okay, those charges there are what's going to drive the membrane to have an electrical potential difference between the two sides. Now, these proteins that insert themselves, they also have what's called ion selectivity and gating, meaning they're going to be selective for which ions can move through them, and they're going to have some gating process to decide whether they're open or not, whether things can move across. So we'll get into more later, like what some of those gating mechanisms are, what causes that gating, but here's kind of an example of that. The big thing here you'll see is this alpha helix domain right here in this protein. Those are the portions that are going to insert themselves into the membrane. Okay, those are the things that are going to make up that transmembrane domain. And then you can see here with these subunits, there's places where there's going to be extracellular spaces and intracellular spaces for things to interact with. And that's going to be key as we move forward with some of the receptors we look at and the channels that we look at. What parts are intracellular, what parts are extracellular, and how does that play a role in its functionality. So other things that are active, you have ion pumps. Okay, again here, they're going to some of these proteins are going to actually actively pump molecules in and out, different ions in and outside of the cell. For instance, here we have the sodium potassium pump. Okay, that's using ATP. Okay, and it's sending sodium outside the cell and pulling potassium back inside the cell. Active energy process. Okay, actively moving things from one side to the other. Okay, so it's got an enzyme that's going to break down ATP when sodium is present, and that, like I said, that's going to actively get sodium back outside the cell into the extracellular space and bring potassium back into the cell, into the intracellular space. And you'll see when we get to the action potential why that's really an important thing to have happen. It's also going to be calcium pumps, which is actively going to transport calcium outside of the cell. We need to keep calcium concentrations low inside the cell for functionality, for a lot of second messenger things that happen inside cells. Okay, so how do ions move? Well, one way they can move is diffusion. Dissolved ions are going to distribute evenly, obviously. If you open up a gate, they're going to start to move across. Okay, and eventually they'll hit some kind of concentration gradient where the concentration will be equal on both sides, right? You'll have the same number of sodium ions as one side as the other. Okay, so that's great. Diffusion is going to kind of passively allow things to move one way or the other. But in the cell, what happens? We end up with what's called a resting membrane potential. That is the difference in charge from one side of the membrane to the other. Okay, so you can see here they kind of zoomed in on it. There's excess negative charge on one side of the cell and excess positive charge on the other side of the cell. And the difference between those two sides is this right here, which is minus 65 millivolts. That's approximate. Lots of cells rest at different potentials than that. But if you have a cell that's completely inactive, it's probably going to be around like minus 60 and minus 70. based on whatever the concentration of ions is inside and outside the cell. But that's kind of normal rest for a cell inside a body. So they basically took, what they're doing here is, this is a little glass electrode. You stick it inside a cell, it's got a wire inside it, and then you have a ground point outside the cell, so you can compare the electric potential between those two things. And that'll tell you the charge difference, which is kind of the drive on ions to move from one side to the other. We'll talk about that in a second. So in the membrane, you end up with reaching what's called an equilibrium potential. That is where there is no net movement of ions from one side to the other of the membrane. Okay. So for instance, here we have a high amount of potassium inside the cell, right there, okay, and a low amount of potassium outside the cell. Okay. Initially, there's no protein spanning that membrane, so they're kind of stuck there. Okay. However, when we put in a potassium channel right here, okay, potassium starts to flow outside the cell, but there's a higher concentration of positive charge outside the cell. So even though potassium might be moving this way based on its concentration gradient, so K, big K to little k, because outside the cell is more positive, and you have a potassium that's moving into that positive direction, that's going to slow it down, right? You're not going to have a positive charge move into a positively charged location, because those charges are going to work against each other. So there's this kind of tug between the concentration gradient and the charge of the ion to determine when we're going to reach that equilibrium point, where the rate of flow of ions in both directions is equal with that channel. Okay, so again, equilibrium potential is the point where the flow of potassium inside the cell or outside the cell is exactly equal to the flow of potassium back inside the cell. And for potassium, that point is going to be where the concentration of potassium is actually trying to still push potassium out of the cell because of that excess positive charge over here on that side. Okay, so again, you're fighting between two forces, right? You're fighting between electrical force and you're fighting between a concentration force trying to drive it one way or the other. So when we reach those equilibriums is going to be based on how easily the ion can move from one side to the other and the concentration of that ions on both sides of a cell. So for sodium, for instance, here, okay, you have sodium has a higher concentration outside the cell, lower concentration inside, higher negative charge here, outside the cell, okay, attracting sodium to it. Okay, sodium's not going to want to move outside the cell in this case. Sodium's going to want to go inside the cell, okay, because of concentration, okay. Sodium's going to want to stay outside the cell because it's going to be attracted to this negative charge over here, okay, outside the cell. But the huge concentration difference is going to drive sodium into the cell initially until you reach a point where the positive and negative, that high positive charge inside is going to keep sodium from rushing in. Okay, so hopefully that makes some sense. We'll go through it a little bit more together, but again, you're looking at the balance and the playoff of concentration gradients making things move and electrical charge interactions pushing things and repelling things away from each other. So what you're able to do is actually calculate the exact value of the equilibrium potential for each ion in millivolts. So that takes into account the charge of the ion, the temperature, okay, and the ratio of the external and internal ion concentrations with this thing called the Nernst equation. We'll see in a second. Don't worry about mathematically getting it. The goal is to understand kind of what it sets for each individual ion. But just for those of you who might be interested, here's the formula right here. So the equilibrium potential, the membrane potential, is equal to the gas constant R times the temperature in Kelvin over Z, which is the number of electrons, meaning the charge. So for instance, calcium would have a Z of 2, and sodium would have a Z of 1. Okay. Um, so yeah, and then it's based off the natural log of the ratio of the two concentrations, where X is a concentration outside, X out is a concentration outside, and X in being a concentration inside. Okay, great. It's not too complicated equation. You can do the math. We could do all that stuff. We're not going to, but just understand that sets that equilibrium potential. So for potassium, it's if you had a concentration outside about 5 millimolar, and these are pretty close to what they are, reasonably there. Okay, concentration inside millimolar of 100, you have an equilibrium ion reversal potential of minus 80 millivolts. Okay, what does that mean? Okay, and why did sodium has a concentration of 62 millivolts, or equilibrium potential of 62 millivolts? Calcium is 123 millivolts. Okay, what does that all mean about the cell? Well, what that means, if the cell is at minus 80 millivolts, okay, that is the point where potassium will not move back and forth net, or net, there'll be no change. Okay, so potassium is super happy when the cell is at minus 80, it's just moving back and forth equally both sides. If it's at minus 70, okay, it's going to try to bring it back down to minus 80. If we're up at plus minus 40, minus 30, minus 20, it's going to try to bring the membrane potential back down to minus 80 millivolts. So say if we were to chart out the membrane potential was going up, okay, for some reason, maybe electrically we changed it, potassium would try to bring it back down to minus 80. So say it was right here, minus 70. We brought it up here to minus 40. Potassium's going to try to bring it back down to minus 80. Now, we talked earlier, we said cell resting membrane potential might be minus 65 millivolts. Okay, if we all of a sudden let sodium start moving across the cell and it has an equilibrium potential of 62 millivolts, that membrane potential is going to skyrocket, trying to reach 62 millivolts, trying to get to potassium and sodium's equilibrium potential, assuming it's the only thing flowing. Okay, and we'll get into more later when we get into the action potential, but kind of understanding that equilibrium potential is kind of what's called the reversal potential too, meaning that if you are above minus 80, potassium is going to go from inside to outside. If you are below minus 80, potassium would actually go the other way. Potassium would actually go outside the cell. For sodium, it's at, if you're below 62 millivolts in this case, everything's going to rush inside the cell. If you were above 62 millivolts, things would rush, sodium would actually go outside the cell, even though the concentration is so different. Even though there's that really high concentration outside, if you went above 62, the electrical force would actually push sodium outside the cell against that concentration gradient. Again, we'll mess around with that. We'll talk about that some more when we get to the action potential, because that plays off a lot on these. But just to understand, potassium's reverse potential is really negative. Sodium wants to be up here at plus 62. And calcium, another big role player there, wants to be actually at 123 millivolts for the resting membrane, the membrane potential for equilibrium. Okay. Now we can combine all three of those into what's called the Goldman equation, okay, which deals with what's called permeability and the different ion concentrations, and actually plays off all three of those major ion players, sodium, potassium, and chloride, to determine what is the membrane potential of this cell, or what should it be based on the different concentrations, and also how permeable the membrane is to each of those ions. Again, don't worry about doing the math here. We're not going to do that. But just understand there is that ratio there that allows us to predict which direction the cell is going to move based on which direction the ions are going to move based on the membrane potential of the cell. So what this tells us, if we're at rest at minus 70 millivolts, basically what's driving the membrane potential to start? Well, it's potassium. Okay. At rest, potassium is a key determinant in resting membrane potential. It wants to be about minus 80. Most of our cells are down around minus 70, minus 65. meaning that at rest, you have potassium channels almost freely flowing back and forth, very close to their equilibrium potential. There may be some sodium flowing back and forth in small amounts that raises it above that minus 80 or minus 70, wherever the equilibrium potential is for potassium, but for the most part, you have sodium. One of those kind of potassium channels that's open at rest is what's called the shaker potassium channel. They cloned it in fruit flies. And basically, this fruit fly, if you deform this channel, it can't maintain its normal resting membrane potential and just shakes everywhere. So it walks around just jittery. So these potassium channels, pretty important. They're extremely important. Okay. Roger McKinnon actually won the Nobel Prize for it back in 2003, looking at specific types of potassium channels that are inherited in neurological disorders. Again, they're usually going to be 4 subunits, okay, combined together, and they have very high selectivity to just potassium. Sodium's not going to flow through it. And it's all based on this thing called the Poor loop here. That's what's going to give us our selectivity, okay? The extracellular, intracellular domains, these loops on the outside, okay, they're going to provide maybe some regulatory effects, okay? The alpha helices are going to create the part that actually can go through the membrane, but that Poor loop, that's going to be the key thing that drives whether or not that channel, what that channel is selective for. So again, here's kind of a graph of that. As we increase concentrations outside, you can see that the membrane potential shifts upwards, okay, meaning that we are changing that membrane potential by increasing concentration, getting rid of the concentration drive. Normally, concentration drive for potassium is outside the cell or from inside to outside. So if we increase the extracellular potassium, okay, obviously we're going to change the membrane potential because we're no longer having potassium we're no longer at the balance, the electrical balance for potassium. We're messing with that. So some other ways you can maintain the resting membrane potential are all the astrocytes that are around. They're going to absorb and regulate the external potassium concentration. And you're going to have things like the blood-brain barrier, keeping things from outside the brain from getting inside the brain and messing with those really important concentrations we need to maintain. So all of these are extremely important. All of these processes together, they're not super active in terms of energy consumption, except for the sodium potassium pump, but really that's only really necessary when we start to mess with those concentrations of sodium potassium. That initial membrane potential is extremely important to set us up for all the other activity we're able to do electrically in the cell, which we'll get into when we talk about action potentials.